Let's move on to the third presentation, which is going to be remote. The third talk is about watching your call, breaking privacy in LTE or 5G networks. We have Zishuai Cheng, who will be presenting remotely.
Okay, thank you. Welcome, I'm Zishuai. Today we represent our work, watching your call, breaking VoLTE Privacy in LTE 5G networks. This is the joint work collaborates with Mihai, Flario, Daojiang, and Dominic. So the VoLTE is voice over LTE, which is similar to the VoLTE. VoLTE uses the SIP message, SIP protocol to manage the call session, and use the RTP protocol to transfer voice data like this. The goal of our work is to monitor victims' VoLTE activity and retrieve victims' images and link the victim's identity to their phone number. To do this, we need to collect victims' uplink and downlink traffic on the air and distinguish their types, like this is internet traffic, this is SIP signaling traffic. We set up a mobile relay to do this. We need to map the encrypted signaling and voice traffic to specific SIP signal and voice activity. We do this use the VoLTE metadata. We also need to force the call network to reach victims' images. So here is a demo video of our work. Starting the mobile relay. The victim UE is connecting to the mobile relay. Obtain victim's TMC and image. Now we are setting a VoLTE call. The conversation is started. Those are the traffic collected as a mobile relay. Now we are analyze the SIP signaling log. And the conversation activities. So the mobile relay is a software component which is built on top of SRAM and is almost undetected. The mobile relay passively monitors encrypts the radio link between UE and LTE 5G networks. So the UE and the base station are usually connected use the radio link. This link is protected by ACA, EA, and EIA. Our mobile relay breaks this link into two parts, like A and B. We forward the message between A and B as PDCP layer. Here is the air interface protocol stack for the lower layer, like PHY physical layer, MAC layer, RLC layer. The mobile relay maintains independent connection for each layer. But for the user plan data layer, user plan data and control data, because those data are encrypted at PDCP layer, so we just forward those data at mobile relay. But the mobile relay can distinguish this message using LCID, which is the logical channel ID, which is planted on the air. However, it's difficult to maintain the radio link at mobile relay because manufacturers could break the connection. Specifically, the physical layer parameters are lost because the MAC layer is configured from the RC layer using encrypted message. Those parameters are most time and frequency domain parameters. Without those parameters, the InnoB cannot pick up the uplink data. Actually, one of our contributions is to recover those encrypted parameters. Now I will introduce how to calculate the physical layer parameters. The mobile relay determines if the victim's physical layer were updated by examining the packets of the link message. And we use the following procedure to calculate those parameters. We first open our proper resource block and waiting the UE to use one of them. Once the first message arrives at mobile relay, we know the frequency domain parameters, but for now we don't know the time domain parameters because we only know the subframe number of this message. We don't know the periodicity. So we know this message and wait the UE to send another message so we can calculate the periodicity. After we got the frequency and the time domain parameters, we do some clean work at mobile relay, like close reduction RBs and updates parameters on both InnoB and UE side of mobile relay. Actually, during the calculation, we need to address signal interference to identify if this message is sent by victim UE. So in this work, we use the TA, which is time advance, and SNR signal noise ratio to do this work. Here is a distribution of TAs and SNR observed at mobile relay. The TA of this victim's UE's message is almost 0, and those messages also has a higher SNR value. So we can use the TA and SNR to distinguish those messages. Now we move on analyzing VoLTE activity. Here is a simplified VoLTE diagram. After established DRB1, the DRB2 is established for transferring VoLTE signal if VoLTE is supported. When making VoLTE call, the SIP message is first changed to establish the call session, and the DRB3 is also established to transfer voice data. So by expecting the traffic transfer on DRB2 and DRB3, the adversary can monitor victim's signal and conversation activity. In this work, we use the metadata of RTP packets to monitor victim's conversation activity. Specifically, we use the encoding schema and the comfort noise. In LTE and 5G, the VoLTE or voice over AR use adaptive multi-rate wideband to encode audio data and generate phase length packets. And they use the VD, voice activity detection, to save the bandwidth and improve calling quality. The comfort noise frames are the special frames which contains background noise parameters, not the real audio data. And they are generated only when VD detects that the speaker has not spoken in last sample period, like 130 milliseconds. So therefore, we can use the uplink and downlink bandwidth, specifically the packet size and the frequency, to recover victims' conversation activities. Here is an example. At the start, the packet is significantly bigger because LHC is not established. The blue point here indicates the victim was spoken in last 20 milliseconds, and the magenta points show that the victim was not spoken in last 130 milliseconds. Now we move on recovering victims' SIP signal log using direction, size, and sequence information. To do this, we need an offline work to build a mapping model. After that, we attack a line on mobile relay. To do this, we need to reassemble the encrypted SIP IP packets and calculate transport political context. After that, we identify the safe message by examining direction and size. Now we have the uplink and downlink data, and we have the safe signaling and voice activity. So now, before going to introduce map identity, I will introduce how to get victims images. This only works in LTE. In LTE, the attached requests prefer to use good-in-stat images to prevent information leak. So we propose to manipulate the victim's identity contained in attached request message in this message. Because the value is invalid on call network, so the UE will restart the archive procedure. The mobile relay can retrieve victim's image in the following plain text identity response message in this message. So to associate victim's image with her phone number, we need to comparing VoLTE log. To do this, we need to send a safe message to victim's UE to trigger some VoLTE activity. And we use the recovered VoLTE log like this to link victim's identity to her phone number. So now I will introduce that this still works for 5G. We know 5G have two deployment options, 5G standalone, 5G SA, and 5G NSA. The 5G SA is similar to the LTE, so the mobile relay is also worse for 5G SA. But for 5G NSA, because its ISH procedure is significantly different, we think this is a good defense against our attack. To conclude, in this work, we propose physical layer improvements, and we discover the privacy vulnerability of VoLTE, and we propose a method to link victim's identity with phone number, which requires just one safe message. Okay, thank you. I would like to answer any questions, and my colleague Mihai also in the conference. Thank you.
Thank you, Zishuai. We have a question online from Marco. Can it be possible to detect the presence of the mobile relay, either by the mobile terminal or by the network?
I think it's impossible, because the mobile relay he will bypass the archive procedure, and all the message we forward between the UE, the victim UE and the commercial network. So the mobile, both the UE and the Inobi, they will not observe their the network interrupt or something like that. So we think it's almost undetectable.
Gotcha, thank you. And I also have a question, like what's the cost of conducting this attack? Like, do you need to buy special equipment?
Sorry?
What is the cost of conducting this attack? Like, do you have to buy special equipment to be able to act as a relay?
Mihai, can you help me to answer this question?
Hello, everyone. Yes, so the answer to that question is no. It's a very cheap attack to deploy. We took some time developing the software, but the software is out there. We actually weren't the first one to do it. And then after that, you just buy a couple of SDRs. They're relatively cheap. You can get the ones we used were around £1,000. And then you get 2 of them, and then you're ready to deploy the attack.
Let's thank the speakers. And
Thank you.